Alrighty, in this section, we're actually going to look at the effect of both electric fields and magnetic fields on charged particles. And the electric and magnetic fields are actually turned on simultaneously, right? So this is going to be a simultaneous application. Okay, so these applications actually had some far-reaching ramifications actually fairly early on, right? So sort of crossed electric and magnetic fields were used by J.J. Thomson in the discovery of electrons, and to determine their charge to mass ratio. And that was in 1897 that the electron was firmly discovered by Thomson. So again, using electric and magnetic fields in combination, sometimes what is called crossed electric and magnetic fields, because as you're going to see, when they're perpendicular, certain magical things can happen. And later on, crossed electric and magnetic fields were used to discover positive charge carriers, or the signs of charge carriers. Okay, so initially this was done in 1879 by Edwin Hall. And so consequently, this is called the Hall effect. And later it was used to discover, as I said, that not only electrons or negatively charged carriers are important, but also one can have positively charged carriers. And it's only with that discovery and capitalizing on that discovery that we could form transistors, that we can make transistors, and hence have all the electronics that we have today. So the Hall effect was a key experiment in those discoveries. Okay, so we're going to look at a foundational problem first, right? So let's take a look at that. So we're going to have our infamous parallel plate capacitor arrangement, and we're not going to concern ourselves with how that was charged up, but we know that we could do that by connecting it to a source of a potential difference, or an EMF, and we've dealt with that in some detail in previous sections. And so likewise, we know that there's an electric field which is homogeneous between the plates, as long as the plate separation is small compared to the extent of the the plate geometry, and so if the plates are large compared to the separation, then what are called fringing effects are minimized, and the internal electric field is constant. And so let's take a look at what happens when we would fire an electron. Right. So this is an electron of mass m sub e, charge q sub e, and we shoot it in with some velocity. Now, you know that the electric force is equal to q times e, and since q is negative, f of e and the electric field are anti-parallel, or they're 180 degrees with respect to one another. So as this particle enters the field, it's going to experience a force. It's going to be in this direction, which is 180 degrees with respect to the electric field. Okay, and what will happen then is that the resulting trajectory will look something like so. Depending on the speed, it may actually exit the plates, in which case once it's out here, it's going to travel in a straight line since it's no longer acted upon by the electric field and hence the electric force. So that's a problem that we fairly well understand. Okay, and we already went through the charged entity in a magnetic field. That's pretty fresh in your mind. So now what we're going to do is we're actually going to impose. Right, we're going to impose a magnetic field which is oriented 90 degrees to the electric field. And so let's get a magnetic field which is into the plane of the paper, like so. All right, so this is magnetic field into. I'm sorry, color's a little bit hard to see, but I wanted to discriminate here all the things that are going on. As a matter of fact, let me redraw this scenario so that it's a little less cluttered. So here we have our parallel plate capacitor. We have electric field. So we'll use both these diagrams concurrently. So what would happen then is that the electron as it enters this magnetic field is going to feel a magnetic force, and that magnetic force is going to be oriented downward. Right? That's the magnetic force. Right? And so the magnetic force is going to be QVB, QVB sine of theta. Theta is equal to 90 degrees. And so the magnetic force in magnitude is going to be QVB. The right-hand rule is going to tell us that it's in the negative y direction, right, as it enters the field. Okay, so it's going to be in the negative y direction. So that's the instantaneous magnetic field as this object enters the magnetic field. So electric field is going to be in the upward direction. As it enters the field, the magnetic force is going to be in the downward direction as it enters the field. The resulting trajectory of the magnetic field alone, again, would be circular. Okay, so it might look something like that, like so. All right. But what happens now? Right? What happens if we can adjust the electric field and the magnetic field such that as the particle enters the region of space where these crossed fields exist, right? So here's the magnetic field, here's the electric field, and so now our charged entity, our electron, is going to enter this field, okay? And we're going to now adjust. We're going to adjust parameters, adjust E and B, right, such that there is no net force on the charged particle, in this case an electron, right, as it enters the fields. Okay, so what we're going to have then is we're going to have a situation where, given this figure from above, F net is going to be then F electric minus F magnetic. And if we want that net force to be zero, right, by design, right, we want that force to be equal to zero, then F electric then is going to be equal to the force magnetic. And so then this will be Q VB in magnitude. We already took care of the sign up here. This is going to be QVB. Sorry, what am I doing here? So this is going to be Q times E. This is going to be QVB. The Q's will cancel, so it really doesn't matter what the sign of the charge is, right? Or how large that charge is. The charge will cancel, and we get a rather simple but beautiful expression relating the speed with which that charged particle enters, the electric field strength and magnetic field strengths in magnitude. And so V is going to be equal to E over B. It's a really wonderful equation. So what happens in that case is that if that magnetic field and electric field are adjusted, right, the particles go through unscathed and will exit out at the same speed that they exited in with. And so you might say, well, why is that? Why even do that? Why build this elaborate device of having crossed electric and magnetic fields only for it to have no effect? And there's an interesting example here, right, that we could look at. So again, I'm going to draw this gizmo one more time. Okay, so here we have our positive plate. Here we have our negative plate. Okay, here we have our electric fields. And here we have our magnetic fields. And they are at 90 degrees with respect to one another. Right, so E is perpendicular to B. Now, it's very hard to get electrons with a precise speed. As a matter of fact, you might say, how does one get a beam of electrons in general? And again, that's that's tricky business, but one can imagine, right? One can imagine that we have, some sort of metal here, right? Some sort of metal that we heat up high enough that it boils off, literally boils off electrons. And they don't all come off at the same speed off the surface. Just like when you boil water, the water molecules coming off a surface of a pot of boiling water are not all at the same speed, right? They come off with a distribution of speeds. And, that distribution, could be quasi-Gaussian, okay? It's not really Gaussian, but let's just pretend that it is, okay? So it has some average velocity, some average speed. It's got some that are, higher, got some that are lower. So there's some distribution of speeds with which these electrons come off. Now say out the other end, right? We really want to have electrons coming out the other end, which forms a beam of precise speed. Because if we know the precise speed, then we know the precise kinetic energy. And this is needed sometimes when we're doing perhaps what some of you might know in sort of medical procedures. One can do electron beam or proton beam therapies. And that's for cancer treatment. There's a very big proton beam facility over at the University of Pennsylvania, and it's really good for treating, some cancers. Actually has a very good efficacy. But in order to do that, you have to know how much energy you're depositing at the tumor site. And so one can imagine here that one can send this distribution of electrons through this crossed electric and magnetic fields. One can put a shutter down here with a really narrow hole, right? This is sometimes called a collimator, since it collimates the beam. And so electrons are going to enter, since they have a distribution of speeds. Some will be affected more by electric fields. Some will be affected more by magnetic fields, depending on the speed. And for that special speed, which is governed by E over B, so we can dial in E, we can dial in B to be able to get out a speed which is very precise. They're the ones that are going to come through unscathed, and that's going to form this beam of electrons that can be used for therapy, perhaps, right? Or for some other kinds of experiments. So this device then is sometimes called an energy selector, right? Because it can select a beam of fairly narrow distribution in the energy of the particles that are coming out. So the energy selector, a really nice application of crossed electric and magnetic fields, and again with a medical application. Okay, I'm going to end that discussion right there, and so we'll pick it up with the force on a charged carrying conductor, a wire of charge, and we'll pretty much end that chapter with that discussion. All right, take care. Thank you.